Thanks for joining me today as we look through my submission to the Audio Engineering Society Student Design Competition. The inspiration of this project came from the desire to create and design a methodology that would help lower the amount of waste coming from the field of audio engineering. Well, some of you may be asking, what exactly is that waste? Well, every year the world produces 35 million tons of electronic waste, and part of this is due to the issue that many appliances are thrown away when they could be easily repaired. So it is important then, with these figures in mind, that we look at audio engineering, a field that greatly relies on a wide variety of products, from consoles and microphones to processors and even just the computers used to run studios. The world of audio engineering uses a lot of electronics, and we need to be smart with how we are taking care of and potentially disposing of these items. To help demonstrate a design that combats this waste, I converted an old outdated radio into a guitar amp. By creating this design, I was able to accomplish multiple goals at once. For starters, this design showcases a methodology that emphasizes reusing materials from the start of pieces of equipment rather than creating everything from brand new materials. This helps not only lower the carbon footprint of production by relying on already built materials, but lowers production costs by not having to buy brand new items. This also keeps what was potentially an antiquated and outdated piece of technology out of landfills by repurposing it and giving it new life. And the other important part of this design showcases a layout and promotes longevity by making an easily repairable and reusable piece of musical equipment. Time was put into this design to ensure that when a part went bad, it was easily repairable and would not cause the entire product to need to be thrown away, as is the case now with newer items and current philosophies. So, how did this look? Well, to best showcase this methodology and design, the right amp layout had to be chosen to work off of. I chose to look at this through the 5C2 Fender Princeton and then modified it to better fit within the constraints of my build. By using and adapting the schematic, I was able to reuse original parts from the radio and create a layout that would allow for easy maintenance and repairability over the amp's lifetime. So, when designing the amplifier, there were multiple modifications I did to modernize the circuit, along with making sure the amp layout was implemented in a proper and efficient way. Starting with layout design and signal flow, the most important thing this design needed to showcase was ease of repairability and servicing. That's why when you look at the layout, you can see the areas of the amp, such as the preamp, output stage, filtering, and powering, are all in distinct areas and easily identifiable. This was to make sure the next person looking at it could easily see and identify problems through working through these distinct areas. All parts were then hand wired and made easily accessible to ensure for fast and efficient component swapping. After this, going through signal flow, it was also important to have good separation of power and signal wires. This was to make sure hum was minimized and a good signal to noise ratio was maintained. In terms of modification, the most important one started with the lowering of the secondary winding voltages. When originally built, the United States wall voltage was lower, as evidenced by notes on the original Fender schematic. It was important to take note of this because this design was built to accommodate and reuse new old stock, and used tubes to keep the build's production footprint low. Because of this, those tubes need to see a lower plate voltage and not work the high voltage we now demand of new production. After this, I also made a small but important change of switching the order of the three filter capacitors. Originally, the 16 microfarad capacitor was placed at the third and final stage of filtering. I switched it to the first stage instead. This was important to help increase the frequency response of the amp by tightening it up. Finally, I made another small change of using metal oxide resistors rather than the traditional carbon composite resistors at the input jack and power stages. While I wanted to use new old stock resistors when possible to keep with the idea and theme and ability of reusing as much materials as possible, metal oxide resistors are far quieter than their carbon counterparts and would help to lower the noise floor by getting rid of unwanted hiss at the input and power stage. So to see what this all ultimately culminated into, here's a video of me playing the amp at a recording session. The sound you're hearing is a Fender Stratocaster going directly into the amp and being recorded by a Royer R121. As you were able to hear and hopefully see through this presentation, the goal of this design was met. An amplifier was created that was able to fit into a repurposed housing and reuse the original components when possible. And an amplifier design was created that highlighted repairability. All of this helped to keep production costs and carbon footprints low while enabling a design that would extend the amplifier's use and lifetime well into the future. It is my hope that by showcasing successful designs like this one, audio engineers and audio companies can place emphasis on creating products that are greener for the environment by being built to last, not being built to be replaced. Thank you for your time, and I hope you enjoyed this presentation.